What's up, everybody? My name is David Wilson, and welcome to the Dev Aspect. In the previous episode, we designed a basic data model for our simple text-based adventure game. In this episode, we're going to use that data model plus some of the things we learned in episode 1 about functional programming to make some basic game logic for our adventure game. Specifically, we're going to use function composition, partial application, and pipelining, along with another feature in F# called the match expression, to start to build layers of logic, or at least the code that can allow us to transform the state of our game world. As we discussed in the first episode, functional programming languages are primarily based around immutable data structures. So what we're going to show is how to maintain immutable data structures through various different state transitions and transformations in the game logic. I expect this episode is going to be a lot more interesting than the last two because the code that we write is going to be quite a lot more substantial. There's also the chance that it could be a bit more advanced than what we covered in the previous two episodes. So if there's anything that I talk about here that wasn't explained clearly enough or is sort of confusing, please feel free to leave a note in the comments so that we can talk about it and maybe I can cover it on the next episode. One other thing I should point out, in the previous episode, at the very end, I mentioned that we'd be covering the actor model in this episode, but since there was so much to cover in the coding part here, I decided to go ahead and push that to the next episode so that we have plenty of time to go into detail about the things that we're going to talk about today. So since we have a lot of things to cover in this episode, let's just jump right into the code. So let's get started by reviewing the data model that we created in the previous episode. It turns out that we need to make a couple tweaks to this data model to make it appropriate for what we're trying to accomplish by using more functional patterns to do our game logic design. The most important thing to note is that previously we were storing the room object inside of the exit information. And as I started working on the code for this episode, I realized that by doing this, we actually are going to be carrying around multiple copies of our room information. And that doesn't work for what we're trying to accomplish by using functional principles and immutable data structures to construct our game logic and our data flow of our game world states. So the biggest change is that now we have this concept of a room ID. And we're using this discriminated union that actually has one case, room ID of string, just so that we have a more specific data type to represent a room ID in the domain model of our game. And you can see that the exit discriminated union type now refers to room ID in the passable exit case. So now we're just referring to an ID for a room rather than carrying around the room object itself inside of the exit. Another thing to note is that we've added the world type. And the world actually has all of the rooms set up in a map, which is basically like a dictionary, where you are mapping between the room ID to the actual room instance. And this is what's going to allow us to change the state of the rooms when things happen, like the player moves between them, or if the player picks up an item in the room. And it allows us to have one central place, one central source of truth for the state of every room in the game world. You'll also notice we have a new player data type, which just contains details about the player, its current location, represented by its room ID, and the list of objects that the player has in their inventory. So now that we've sort of covered the changes to our previous data model, we can go forward and build some logic code based on these data types. Another thing that I've done is actually create an initial game world, which basically I've just defined a list of all the rooms in the game that have some descriptions, some exits, and then I've put them together in a list. And then I've also created the map for the game world. I've created the main game world object, which has all the rooms, and I've basically used pipelining to convert that list of rooms into a map based on the room ID and the room object for each room. And then I've also created a player. His name's Luke. He has a description of just your average adventurer. So we put those things together into the game world object, and now we're going to use this as our starting point for writing all of our game logic code and manipulating that game world. So the goal with our game logic is that we want to try to define something like a pipeline where we have an initial state of the game world, and everything that happens, every action that takes place in the game world, takes the current state of the game world, does some transformation on it, and then returns a new state of the game world. So this fits back in with the whole concept of immutable data structures and not having sort of shared mutable state, because we're not keeping the same object of game world state for each action that happens in the world. We're actually taking the previous state of the game world, manipulating it, and then returning a new state. So here's what that might look like. So imagine we start out with our existing game world object. Then we pipe it through something like move north. Then maybe we might pipe it through something like move south. And then we might pipe it through another function that can give us a description of the world. So describe current room. So this is what we're going to be shooting for in this episode. We're going to try to make this sort of pipeline of transformations and then other helper functions work. So the simplest thing to start with would be to try to define this describe current room function. So let's try to define that now. And we're going to give it the parameter of world as its sole parameter because we're passing in the game world. So basically every function that we have that transforms the state of the game world at any moment basically will take in an instance of the game world record type and then return a new instance of the world record type. So if we have the world, we're looking for the current room, and we know that the current room is defined based on where the player's current location is. So we can say world.player.location. So now we have the location, which is represented as a room ID. So next we need a way to be able to get the room that the player is currently in. So we're going to pipe that through a function that we will call getRoom. And since we're piping the location through the pipeline, we're going to say pass in world as the first parameter of getRoom so that our pipeline design is correct, and the second parameter ought to be the room ID that's coming through the pipeline. So we can go ahead and start writing that function now. So we know that we have a map in the world record type that contains all of the rooms mapped by their room IDs. So what we'll do now is try to extract the room object based on the room ID. And we're going to use a try find method because in some cases we may not actually have the proper room for the room ID. So we need to try to see if we can find it. Okay, so now we have the getRoom function, which can find a room based on the room ID. We have describe current room, and then we're using getRoom to find the room. So lastly, we're going to need some way to actually describe the room that we get back from getRoom. Since we know that room has a details object, and all we really need to be able to do is just write out the details of the room, we will use an anonymous function that will take that room, get the details, and then run it through a new function that we're going to write called describe details. So now we see that our describe details function is not defined yet, so we'll take care of that in a second. So now we can see that we have a red underline. If we hover over that, we see that our describe details function is not defined, so we'll go ahead and try to write that now. So let describe details, then we'll take in a details object. And now we'll use the printf function so that we can print this information out to the screen. And we'll add a couple of new lines in just so it's more obvious. In fact, let's add a couple more here just to make it really clean. And here we can write the details.name and details.description. So now we see a new error. And it says that the option type for room is not compatible with type player. And at this point, I think it's basically just getting confused between the player and room types. But the bigger issue that we have here is that the try find method actually returns an option type, which means that it will return some room or it will return none based on whether or not the map actually has the room that corresponds to the room ID. So this is the first point where it becomes obvious that we need some way to deal with the cases when the result of some function can't actually be used. And technically, we're going to call that like a failure state. So what we need in this case is some way to extract the room from this option type whenever there actually is a room, and then to be able to do something constructive whenever there's nothing returned, so that the player knows or that the game logic knows that we can't actually move forward from here. So let's write a function for a sort of temporary use that will help us to extract this option. So let's say extract details from room and room. And this is the first time that we're going to check out F# match expression. And the match expression is a really interesting feature of F# that allows you to take an input object and then do different operations based on what possible values that the input object may be. And the other interesting thing is it actually allows you to destructure that input object so that you can extract the information you need from it and also perform some behavior on that extracted information. So let's start by writing a simple match expression here. Match room with, and then we drop down to a line, and then we use the pipe character to denote one of the cases of the match expression. So since we know that room, the value of room would be an option type, we can say sum of R, and here we'll say just r.details because we just want to get the details out. So for the none case, let's just return a bogus details object for now, and we'll find a better way to deal with that later. So what's happening here is that the match expression is taking in the object room, and then it is for each state of what that object could be, which we know is an option type, it will either extract the value of the room and then give the details of that room object, or for the none case, if the option is none, then it will just return a default details object. And one thing that's interesting here is that the type system has determined that player is the core type here in the option, but we know that's not the right thing, so let's go ahead and just set this to make it more obvious. We'll say this is a room option. And sometimes this is sort of necessary in F# type system just to get all of the code lined up first, and then you can go back and remove some of these type annotations so that your code looks more cleaner. But for now, we'll just leave this annotation in so the type system is not confused. So now that we have our extract details from room function, we can go use it to take the room option and return the details to describe details so that it can write out the room's description. So let's go ahead and do extract details from room, pass in the room. Then we can pipe that through to describe details. And since describe details needs a details object, we can just take this room.details out because now we're piping it through. But one of the more interesting things we can do here is actually leverage function composition so that we can turn this into an actual function here in line so that the room option just gets passed straight through this function that puts these two extract details from room and describe details functions together. So to do that, let's just take out the original function information, and we'll take out room too, and then add the composition operator. So basically what's happening here now is that this composition operator is turning these two functions into a function that takes in a room option type as its first parameter, and then returns unit basically because we're going to use printf in the describe details function. So we've taken two functions and we basically just merged them together for the purpose of making them more easy to use. So let's try running all this code up to this point and see if it works. Now let's run our pipeline. Great. So now we can see that we're in a central room, and it describes that we're standing in a central room with exits in all directions. So that's great. So now we actually have the basic part of our game world pipeline started. So now let's move ahead and try to make the functions that will allow the player to move between rooms in the game world. And as we had described before, what we want to be able to do is have a function that's like move, and then it says what direction it wants to move in. So let's say move south. Now, what we need to have here is a move function. So let's start writing that now. And since we know that we're piping the game world through this pipeline, we need to have world as the last parameter to this function. So the question now is, what is direction? Because if you remember, our exits record type has properties that name all the directions that may have exits. So we need a convenient way to be able to extract an individual exit that we want from this record type. So what we can do is define some functions that are actually capable of doing this. So let's start with the function to go north. So what we'll do is use something called parameter destructuring so that when we're given an exits object, we can actually extract the north property from that record type. So what we're doing here is we're saying by using the curly braces as our first parameter, we're saying we want to destructure a record, and we want to take the north property and we want to assign that to a new variable in this function, or a new binding in this function called north exit. And since all we want to do really is just get that exit out of the record, let's just return north exit directly. And that's pretty much it. We have a function now that can extract the north exit from an exits object. And if you hover over north, it knows that we're talking about the exits record type because exits is the only record that has a property called north in our data model. So now I'll quickly put together the functions for the rest of the directions. Okay, so now we have all of the functions for our different directions. So let's try to run these and see what it says. So we've got some warnings here that basically say that the field labels and expected type of this record expression do not uniquely determine a corresponding record type. This is true because if we ever had any other record type that had these same property names, then we'd have some kind of conflict. So in this case, it's actually better to be explicit about which record type we're talking about, and we can use a type annotation to accomplish that. So now it knows that we're talking about the exits record type here, and it doesn't give us the warning anymore. So I'll go ahead and fix the rest of the functions to also follow this pattern. Okay, so now that we have our direction functions, we can go on to making our move function work. So in our move function, the first thing we're going to have to do is get the current room that we're in from the game world based on the player's location. So let's go ahead and say world, start a new pipeline. And then we'll say get current room. So now we need to write the get current room function. So let's define that here, get current room. And we'll pass in world because that's really the only parameter we need, because the world object has all of the information we need. So we know that world has the player's location, but we need to be able to get the room object based on that. So we have the player's current location in the world, and we've already defined this get room function, so we can go ahead and use that in this function as well. So now that we've got the current room in our pipeline, now we need to know whether we can move in the direction that the direction function specifies when this function is being called. So what we need to do is get the exit so we can decide whether we can actually move in that direction. So let's make a function called getExit for the given direction. So let's start writing that now. So getExit will obviously take our direction function in because that will sort of define which direction we want to get an exit for. And we also need to have the exits for the room. So let's say we take in the exits object. But immediately we see that we have a problem because getCurrentRoom returns an option type of room, and somehow we need to extract the room from that and then get the exits from the room that was contained within. So now we've sort of hit a problem in the sort of pipeline-based design of piping your state through these different functions, because sometimes there are going to be instances where a previous function wasn't able to complete the operation that's needed for the later steps in the chain of functions. So we need to have some way to deal with that. One option for this is to use a technique called railway-oriented programming. And as far as I can tell, this concept was coined by Scott Vlashin, who makes a really excellent website called fsharpforfunandprofit.com. And I'm going to use bits and pieces of his strategy of railway-oriented programming to make our pipeline work. So if this approach seems interesting to you, definitely go check out Scott's website because there's a wealth of information about this pattern, plus a whole lot more stuff that is really interesting if you want to learn more about F#. So to get started into being able to deal with our pipelines and to be able to effectively pass our results and also errors through that, we need to create a new discriminated union. So let's scroll up to the top here so that we have some space. And let's define a new discriminated union type called result. And will be the first time that we're going to show any kind of uses of generics in F#. So we're going to actually have a success value type and a failure value type. And our discriminated union cases will be success of T success and failure of T failure. So what this allows us to do is to specify that an operation either succeeded with some result value or failed with some kind of error information. And this failure could be any kind of object. It could be a record type that has detailed error description, or it could just be a string. And for the purposes of what we're going to do today, I'm just going to stick with strings for our failure value type. So the first thing we can do once we have this result type is we can change our getRoom method to use those values. And we'll do that by using a match expression so that we can deconstruct the option that comes back from try find and return a success or failure instead. So now we've changed our getRoom function to return a success or failure based on whether the room is found. So immediately after changing getRoom to return a result, we can see that this extract details from room function has got an error under it because the return type's changed. So we'll deal with that one a little bit later. Another thing we can notice is that the getCurrentRoom method also now returns a result because it depends on the getRoom method that we just changed. So now that we've started to depend on this result type, we're going to have to do some things to be able to make these results flow successfully through our world transformation pipeline. So let's try to start dealing with that in our move function that we had started writing. So now getCurrentRoom, like we said, returns a result. And we need to do something that will allow us to take the room out of that result or pass along the error if there was an error in getting the current room, like if the room wasn't found for some reason. So what we'd like to do here is to have a function that takes the room that comes from getCurrentRoom and returns its exits. But since we're taking in a result of room string, then we can't actually do that directly. So the question is, what do we do about the input to this function? Well, for railway-oriented programming, there's this concept of having a bind function that's able to take the result of a previous operation and then apply some function to the success if it was successful, or return its failure, return the previous failure if the previous operation was a failure. So let's go ahead and define our bind method. So we'll say let bind, and we're going to take in a function that can process the success value. And we're going to take the last result. And here we'll use a match expression. We're going to match last result with success S. And then with the success value, like we said, we're going to run process func on it. And for failure, we will just return failure again. We're just going to return the same value as failure. So the interesting thing about the match expression is that it's literally an expression. So whatever path, whatever case we take through the match expression, the outcome after the arrow is what will be returned from the expression and hence from the function bind itself. So if it's a success from the last result, then we're going to return the result of calling process func on the success value, and then that will be returned. Otherwise, if it's a failure, then we'll just return the failure that came from the previous result. So now let's try to use this in our move functions pipeline. So we'll call bind here. And since we already have this function, we'll just leave this in parentheses so that we can sort of contain this function. And now we see immediately that still it's complaining, saying that we're returning a type of exits, but it's actually we're expecting a result because bind actually wants to return another result to move on through the pipeline. So in the case where we have a function that returns some plain result, we need a way to wrap that in a result that can be returned to continue going through the pipeline. So to do that, we're going to create a new function called switch. So let's define switch, which has a process func and an input. And since the idea of this function is to wrap a function that just returns a plain value, we're just going to immediately return success and whatever the result of process func called on its input. So now if we go back down and we call switch here, then it makes this line happy. So now we actually have a function that is able to bind a result that comes from the getCurrentRoom function and then use it as an input to this next line of the pipe. Similarly, the getExit function also needs to be bound because it needs to get the result from the previous step. So we're going to call bind here. And we still need to define the getExit function, so let's go ahead and finish that now. So we'll use the direction function on exits to extract the exit for the direction that we need for this call of getExit. And this will just allow us to return the exit itself, but then we need to do something with the exit. So let's actually use a match expression so that we can act based on the type of exit. So let's say we have a passable exit. And in this case, passable exit has details as its first parameter. We don't really care about that, so we're going to use underscore. And underscore is like a character that lets the compiler know that we don't care about that value, so just throw it away in this case. What we really want is the next room's ID. So let's use room ID here. And since we want to return a result from this method, we can use success of room ID. Now, if the exit is still locked, we're going to have to handle the locked exit case. So for the locked exit, we know that it has a tuple that has 3 parts. So let's just go ahead and throw away all of those, because if the exit is locked, then we know that we can't do anything. So there's really no point in pulling out its details. And we have an error here. And what it's saying is that we have a type mismatch, expecting an exit, a tuple of exit and some generic type A, but then we're given an exit and 2 other generic types in a tuple. And the reason why is because I made a mistake in the previous line. Passable exit, we actually need to put parentheses around this so that the compiler knows that this whole section here refers to one destructuring. Because otherwise, this actually thought that I was having a destructuring of passable exit plus some other property that is in here called room ID. So let's just go ahead and fix that. And go ahead and put the parentheses here. So just remember that if you're using discriminated unions inside of match expression, just make sure to put the parentheses around the different tuple parts. So let's finish this by saying failure. And we'll say that there is a locked door in that direction. Cool. So we have this green squiggle here. And this is another sort of interesting thing about match expressions, which is that whenever you have a discriminated union or any kind of value type where the range of values is known, the match expression will actually let you know that you have not filled out all the possible cases for the values that could be present in that expression. This is actually really nice because it helps you to make sure that your logic covers everything that it needs to cover. So in this case, it tells us that we haven't covered the no exit union case yet. So let's go ahead and write that out now. So no exit only has one field, and we don't really care about it either. So let's go ahead and just use underscore for that. Then we'll say failure, there is no room in that direction. So that's great. Now our getExit function will take an exit from the specified direction using our direction function. Then it will use a match expression to see what type of exit it is, and then return a success or failure based on the result. Now, if we look at the move function, everything seems to have cleared up now. And if we hover over move, we'll see that the result type of our function is a result of room ID. So now we're at the point where we actually have the room ID of the room that we want to move to. So let's add the line now to get the new room. Okay, so now move returns the room that we just got. So we're almost there. So the last step would be to have a function for set current room. And it also needs to be bound because it's going to take in the result from the previous operation. And we also need to pass in the world to this because we're going to change the entire world object to have the player's location move to a different room. So let's define the set current room function now. Let's define set current room. And we're going to pass in the world because we're going to change the world object to reflect the new location of the character. And then we'll pass in the new room object. And this is going to be a case where we're basically just going to edit the world record that's passed in, because since this is an immutable object, an immutable record instance, we can't actually change the object in place. We have to create a new copy of the world object with the changes that we want to see in it. And since the location is inside of the player object, we're also going to have to change the player object. So this is going to be interesting to show how we need to actually change multiple things in the object at the same time. So let's say world with, and this lets the compiler know that we want to change the existing world and only set certain properties. We're going to say player equals, we're going to do the same thing again, world.player with. So we're basically taking the player the player record from within the world, and we're going to change it now with location equals room.id. Great. So now basically we're just changing the world and updating the player, updating the player's location to the room's ID. So now we'll see that there's an error here. And the same problem again, since set current room just returns a new instance of the world, we need to use the switch function to properly wrap it in a result. So let's just do that. Cool. So now move returns the new state of the world. So after all these function calls in this pipeline, we're starting with a world and we're returning a world. So if we go back to our initial pipeline, we can see that describe current room has an underline, and that's also because it doesn't have a binding. So let's add a binding here. And also we need to add a switch because describe current room doesn't return a result. And since now the pipeline returns a result, we need to actually just throw away that result so that we can get rid of this green squiggly. So let's just pipe this finally through ignore. And basically it just throws away the result. It returns a unit. So the one last thing we need to fix is the extract details from room function. So this requires that we change our approach. Since extract details from room is expecting a room option, now it needs to expect a result and handle that appropriately. So the cool thing is that we can actually simplify the extract details from room function, because now, since we know that we're going to receive a result, then we don't need to do anything to destructure it. We're just going to take the room in directly. So really all this means is now we can just say room.details. And in fact, we can even take this part out. And now down here, we need to bind this function. And we also need to run it through switch, because extract details from room only returns a simple value. So we'll also have to do this to describe details for the same reasons. Okay, we had the parentheses in a little bit of the wrong place, but now we've got it all fixed up here. So now describe current room takes in a world and returns a result of type unit. So now our describe function should be working pretty well. Everything should be fixed up. So let's see if we can run all the code and see if it works. Okay, so hopefully what's going to happen here is that we're going to move south in the game world. Then we're going to describe the current room, and it's going to print that out to the screen. Okay, cool, success. So now we've moved south, and we print out the details of the south room, which is called a cold room. So if we go up here and look at the all rooms list, the south one room is a cold room. So we've successfully manipulated the world state so that the move method changes the player's location to the room that's south of their current location, which is the center room. And then we've described the current room based on the world output of the move statement. So we can even sort of layer these things in, because that's the whole point, right? So let's say move north and move west. But now we see that we've got an error here. And this is because we need to use binds on all these methods. So let's throw those in real quick. And then run this again. So now we're in the cozy room. So basically what we've done is we've moved south, but then we've moved back up north again, which puts us back into the central location. And then we've moved west. And now we've written out the description of the west room. So that's great. So basically we have this pipeline of functions that we can use to manipulate the world state, to move the player around, and then based on the current world state, we can write out its description. So at this point, you may be wondering, well, I don't really want to be writing all these binds everywhere. I mean, why do I need to do that? So let's actually define an operator that will simplify this so that we don't have to look at bind all the time. So if we scroll back up here to our bind method, then we can define a new operator, which is arrow, arrow, equal. And let's say it takes an x, which is an input, and an f, which is a function. Then we're going to call bind fx. So basically what this will do is take an input value in, and then it will take a function as the second parameter, which lets us do partial application, and then it will call bind on that function, passing in the input value. So if we scroll back down to one of the instances where we use bind, like let's say in the move function, we can actually remove that and replace it with our operator. And now you'll see that everything works just the same. And if we reevaluate these things, you'll see that we end up with the same result. So we can basically just go through and change all of these instances of bind to use our operator instead, and that makes our code look a lot cleaner. It also makes it a little bit more obvious what is going on whenever we sort of pipe all these operations together. So this is basically an operator for doing basically like a pipeline operator, but with a bind attached to it. So that sort of simplifies our code a lot. And in fact, we can get rid of some of these parentheses around and just make our code look a lot more clean and straightforward. So as you can see, this sort of proves our point from the first episode about being able to use function composition and pipelining to be able to basically make a set of functions that transform information one by one. And it ends up making your code look very clean and very clear to the person who reads it. So, I mean, they basically can just see, okay, there's an operation that's taking a world and it's passing it through all these functions. And then once it's done, it's just going to return the output. So we just use these pipelines wherever we need to have a transformation pipeline for whatever values are coming into a function. And just to circle back around to the whole point behind why we started adding these binds and this result type in the first place, it allows us to start to design our logic at a higher level while still being able to do things like error handling, but kind of keeping the error handling code out of the way. So let's say, for instance, we wanted to move south and then move south again. And because I know the design of the world, I know that there's no way you can move south twice. So let's try to move south here. So what you'll probably notice is that it didn't actually return any room description. And that's because whenever we try to move south twice, we're sort of propagating an error or a failure rather than returning success. So the last thing we can do to sort of make it so that you can see the failures that are coming through is we're going to make it so that you can take that result and print it out directly if necessary. So what we're going to do is we're going to change our describe current room function to not print the string, but we're going to actually let it return the string, and then we're going to use that result to print out either the success or the failure of the describe. So let's create a function called display result. We're going to take in a result, and we're going to do a match expression on the result. For success, we're expecting there's a string here. So we're just going to print the string. And if there's a failure, we're going to print the failure. And now we're going to take this out and then just call display result. We should take the result and then write it out. Though we see that we have an error and it appears that I've used switch here when I actually did not need to. So now we have a whole pipeline that should be able to use display result. So now that we've changed these things, let's go ahead and reevaluate our code, our logic code. And now let's reevaluate the pipeline. Okay, so now we see that we try to move south twice, and it says there's no room in that direction. So basically what we've seen here is that whenever we have a success, it propagates all the way through. And if we have a failure, it also propagates all the way through, and we can display the output. So if we set this back to north, where we know we have a valid move, and try to run it again, then you'll see that we are back in the west room, a cozy room. So we'll also see that whenever you try to go through a locked door, it also has the same effect of saying that there's a locked door. So let's change west to east, because the east direction is a locked door. Let's run this. And it says there's a locked door in that direction. So this basically made it really easy for us to put all of our world processing function in a pipeline and then deal with both success and failure cases. Railway-oriented programming is a really cool technique for being able to pass results of computations and also failure information through your logic pipeline. It enables you to write simpler pipeline code that just gets directly to the heart of what you're trying to accomplish, while still being able to deal with failure states, and helps you to write your code in a way that it allows you to not have to worry about all the failure cases that your code can go through. As I mentioned before, definitely check out Scott Voloshin's blog, fsharpforfunandprofit.com, if you want to learn more about railway-oriented programming. It is an excellent resource, and I highly recommend anyone who's interested in F# should go check it out. So in the next episode, we're going to try to expand the project a little bit further and try to make an actual project structure and not just work in a single file anymore. So we're going to go through F# module system. Also, we're going to carry forward the actor model discussion we're supposed to have in this episode by talking about F# mailbox processor, which will allow us to have a game loop that's running concurrently with other things that are happening in the game code. So that should be really interesting. So I hope you enjoyed this episode of the Dev Aspect. If you did, and you haven't subscribed to the channel yet, click the red subscribe button below so that you get notified anytime I release new videos. So that's it for this week's episode. Thanks a lot for watching, and we'll see you next time.